Hello students, this is Mr. Ezra. Today we are going to talk about how to solve radical equations. We're going to look at many examples of different types of radical equations. So while there's going to be lots of examples, you should notice that some are different than others. But if you look at it one at the beginning and you feel like you could work it out, then pause the video, try it, and then hit play and see if you got it right. So a radical equation, we talk about radical equations, we're just talking about equations that have roots in them, square roots, cubed roots, fourth roots, fifth roots. Um, just like we solve quadratic equations, in some cases by taking the square root of both sides, we can solve radical equations by raising both sides to a power. If there is only one radical in the equation, in order to solve the equation, the first step is to isolate the radical. And that means that anything that is not the radical, that's not underneath the radical, that's not the index of the radical, anything else needs to go to the other side of the equal sign using the rules for solving equations. So we have a -2 here, we would add 2 to the other side. The second step after we isolate the radical using the rules of algebra is to raise both sides to the power of the index. The index is the little number that's inside the radical. Remember that for square roots, the root index is not listed. It's understood to be a 2. So whenever you see a square root without a number there, you know it's going to be a 2. In this case, we have a cubed root of x. We're going to raise both sides to the third power to undo that cubed root of x, and 2 to the third power is 8. There's really a fourth step after you solve. You should always plug your answer, your solution, back into the original equation to see if you get a true statement. So our first real example today, we have 5 plus the square root of x plus 1 under the radical equals 16. Remember, our first step is to isolate the radical. To do that, we're going to subtract 5 on both sides of the equal sign in order to get the square root by itself. After doing this, we now have the square root of x plus 1 equals 11. In order to get rid of the square root, we're going to square both sides of the equal sign so that we can undo that square root. And because the square root of something squared is just the thing under the radical, right? So now we have x plus 1 equals 11 squared, which is 121. Once you've squared both sides to get rid of the radical, you no longer have a square root. You can just solve how you are used to solving equations. If you see a plus or minus, you subtract it. If you see something that's multiplying, you undo it with division, etc. So here we've got x plus 1 equals 121. We're going to subtract 1 on both sides to get our solution. So we have solved for x here. We know that x is equal to 120. That's not really the end of the process. This is the answer that you want to circle or highlight or say, here's my solution. This is the answer. That's it. But you should always go back and plug in 120 for x, to substitute your solution for x, to check to make sure that you got it right. Okay, so I plugged in 120 for x. I first do the 120 plus 1 to get 121. The square root of 121 is 11. 5 plus 11 is 16. And if I end up with the same thing on both sides of the equal sign, then I know that I have the right solution, and I can go back and circle the solution that I got. If I've made a mistake here in solving, I might get an answer, but when I plug it back in, it won't work. So checking is part of the process. It ensures that we've got the right solution or the right solution set. Example 2, we have a cubed root instead of a square root. So we're going to use the same set of steps. First, isolate the radical. This 7 in front of the cubed root of 5x minus 7 is like saying 7 times the cubed root. To undo that multiplication, we're going to divide both sides by 7. When we do that, 7 divided by 7 cancels out. We divide 84 by 7 to get 12. We now have the cubed root of 5x minus 7 equals 12. Remember, in order to get rid of any radical, we're going to raise both sides to the index, which in this case is 3. So we're going to raise both sides to the third power. That's going to undo the radical on the left, and 12 to the third power on the right is 1,728. I'd probably have to use my calculator to get that. Once we've undone the radical, once we've cubed both sides in this case, we're going to solve this just like any other two-step equation. We're going to add 7 and then divide by 5. And once we add 7 and then divide by 5, we get x equals 347. This is our solution. This is what we want to put a box around or highlight or say, hey, that's my answer. But to ensure that we've done things correctly, we want to check our answer by plugging in 347 wherever there is an x. 5 times 347 minus 7 is 1728. The cubed root of 1728 times 7 is 84, and since 84 is equal to 84, we know that we've solved it correctly. We've got the right answer. This one is a little bit different. You'll notice in example 3 that we have two radicals. In this case, there's no way for me to isolate one of the radicals because I have two of them. I can't add, subtract, multiply, divide, anything across that's going to get rid of those radicals. So instead what I'm going to do is I'm going to go ahead and square both sides. I'm going to go ahead and raise both sides to the index. Now this is where you want to be a little bit careful. Remember their index is 2. When you raise both sides to the second power, everything is raised to the second power. So the square root of 7x plus 7 is raised to the second power, which gives us 7x plus 2. The index and the exponent cancel each other out. But in the right side of the equal sign, both 3 and the square root of 3x minus 2 have to be raised to the second power. So 3 is outside, but we still have to raise it to the second power because it's not under the radical. 3 squared is 9. And then the square root of 3x minus 2 squared, the radical and index cancel out, giving us just 3x minus 2. So you want to be very careful when you do this. One of the most common things that students forget is that we have to square everything. And when you square a radical, that's pretty easy. Or when you square a square root, that's pretty easy. It just, whatever's underneath comes out, right? But when you square something that's not under the radical, you have to make sure that you actually square. From here, we're going to start simplifying. And in this case, what I'm going to do to simplify is I'm going to go ahead and distribute the 9 into the parentheses here to get 27x minus 18. And I have to collect my variables to one side of the equal sign. So I decided to subtract 7x to the right side to get 20x. And I added 18 to the left side to get 20. Whichever direction you take your variable terms in, you want to add or subtract your constant terms in the other direction. And now we can simply divide by 20 to get x equals 1. So again, first we squared both sides. Then we simplified first by distributing, then by collecting variables to one side using addition or subtraction, constant terms to the other side using addition or subtraction, and then dividing both sides by the coefficient in front of x to get our final solution. Now, that's what we want to circle, put a box around, highlight. We're done though. Really, we should plug 1 back in for x to see if we got it right. So we've got the square root of 7 times 1 plus 2 equals 3 times the square root of 3 times 1 minus 2. All right, well, 7 times 1 plus 2 is 9. 3 times 1 minus 2 is 3 minus 2, which is 1. The square root of 9 is 3. The square root of 1 is 1, and 3 times 1 is 3. And since they are equal, we know that when we plugged in 1 as a solution, it worked. Example 4. The first thing that we want to do with example 4 is notice that there is a radical on both sides. So we're going to have to raise both sides to the index, in this case 3. Again, when you raise a root to its index power, they cancel out. But anything that's not under the root has to be raised to that power. So 2 to the third power gives us 8. We simplify first by distributing 8 times x, 8 times negative 1 to give us 8x minus 1. We're then going to collect our like terms by using addition and subtraction across the equal sign. So we're going to subtract x to the right, add 8 to the left, and our final step is to divide both sides by 7 to get x equals 2. This is the solution that we're looking for. Once we get our solution, we plug it back in to check and make sure that um, the operations inside the radical and everything outside the radical multiply together to give us the same answer on both sides. In this case, it does check out to be the answer, the solution. I do want to point out that it's super important to check your solutions when you're doing this, especially when you raise both sides of the equation to an even power. Because when you raise both sides of an equation to an even power, it is possible that you may introduce what is called an extraneous solution, or you may introduce extraneous solutions. These are solutions that work out algebraically. You've done the math correctly, you get your final answer, and it worked. But when you go back and plug it in, you end up with an impossibility, something that does not work. You don't really have to worry about extraneous solutions when raising both sides to an odd power. It's still a good idea to plug back in your solution to see if you have got it right. But when you raise both sides to an even power, there is a chance of extraneous solutions. Let's look at some examples where there may or may not be extraneous solutions. Example 5 today. We're solving for x. We've got the square root of negative 3x plus 33, and all of that is under the radical, equals 5 minus x. Our first step when we have only one radical is to isolate the radical. Well, it's already isolated, so now we'll raise both sides to the second power. When you raise 5 minus x to the second power, you are not squaring 5 and negative x independently. It doesn't work that way. You have to square the whole thing, all of 5 minus x, which means that we're going to end up with a quadratic. When you square negative 3x plus 33, the square and the square root cancel each other out. But when you square 5 minus x, you have to FOIL it. Remember, 5 minus x times 5 minus x is the same thing as 5 minus x squared. So 5 times 5 is 25. Negative 5x and negative 5x give us negative 10x, and negative x times negative x is positive x squared. So you actually have to multiply that together to get this quadratic. Now, when you have a quadratic, how do you solve a quadratic? Well, you have several tools to do that. I'm going to recommend that in this case you put things in standard form, which means you want a positive x squared, and you want to bring everything to the same side of the equal sign as that positive x squared. So when we when we have negative 3x and we add 3x across to get negative 7x, we subtract 33 to get negative 8, and now we've got a quadratic that we can try to factor or use the quadratic formula or even complete the square or some other method. But in this case, it factors pretty easily to be x minus 8 times x plus 1, which gives us two solutions. X minus 8 gives us a solution of positive 8, and x plus 1 gives a solution of negative 1. This is where we really have to be careful with extraneous solutions. It is possible that when we plug in either 8 or negative 1, they won't actually work, or one of them won't actually work. So we have to plug them in to see. That is your second step for these types of questions. Check for extraneous solutions using substitution. We have to check both of these solutions. So we're going to plug 8 into the equation and do all of the math on both sides of the equal sign. We get 3 equals negative 3. Well, that's impossible. That's not true. Doesn't work. When we plug in negative 1 on both sides, we do the math. We end up with 6 equals 6. Well, that does work. Yay. Well, what does that mean? It means that 8 is an extraneous solution. We're not going to count it as one of our solutions because it doesn't actually work when we plug it back in. There's only going to be one solution here, and that one solution here is negative 1. It's the only one of the two solutions that when plugged back into the function or into the equation, give us the correct answer, or work out to give us the exact same thing on both sides of the equal sign. It is important to check for extraneous solutions. Here's another example, example 6. Let's check this one out. Again, remember, you can always pause the video and try it on your own to see if you can get the right answer. I notice that my radical is already isolated. It's by itself on one side of the equal sign, so I square both sides. Squaring a radical is easy, but squaring x plus 3 means I have to FOIL it, first outside, inside, last. which works out to be x squared plus 6x plus 9. There is a shortcut to this. I'll share it with you, and I've probably put this in a video in the past, but whenever you square a binomial, here's your shortcut. You square the first part, x squared. You multiply 2 times the first times the second. So 2 times x times 3 is 6x. And then you square the second part to get 9. You don't always have to FOIL it. You can use that quick shortcut of square the first one, 2 times the first times the second, square the second. All right, well, now we've got a quadratic. We're going to get everything on the same side of the equal sign. Remember, x squared this term needs to be positive. So we're going to take everything to the right using addition and subtraction, and we get x squared plus 4x minus 5. Well, this also factors to be x plus 5 times x minus 1. There are two solutions then, negative 5 and positive 1. Using the zero product property, we set both of them equal to 0 and get our two solutions. Are they both real, true solutions? Well, the only way to find out is to plug them into the equation to see if they actually work. So that is step 2, use substitution, check for those extraneous solutions. Well, we plugged in negative 5 into both sides, and we ended up with 2 equals negative 2 when doing the math, and that's not going to work. That's not a solution. On the right side, though, we plugged in 1 on both sides of the equal sign for x, and we ended up with 4 equals 4. Well, that is a true statement. It worked there, so we know that 4 is, in fact, a solution. Therefore, x equals negative 5 is extraneous. It is not a true solution. The only solution is x equals 1. Example 7, one more example like the ones we've been looking at. We're going to square both sides since the radical is already isolated. And that gives us negative 9x plus 28 equals x squared minus 8x plus 16. Remember my shortcut that I told you? Square the first one. Well, negative x squared is x squared. Then multiply 2 times the first one times the second one. Well, 2 times negative x times 4 is negative 8x. And then square the second one. 4 squared is 16. So there's your shortcut, right? You can go straight here without having to use the FOIL process. We've got a quadratic again. When you have a quadratic, you have to solve it using factoring or the quadratic formula. So we're going to get everything on the same side of the equal sign, giving us x squared plus x minus 12. Remember, we're just adding and subtracting using opposite operations. So the opposite of negative 9x is positive 9x. We add 9x to the right. The opposite of plus 28 is minus 28. We subtract 28 on the right. Now we factor. This factors to x plus 4 times x minus 3, which gives us two solutions. When we set them equal to 0, we get negative 4 and positive 3. Now, I have to check to see if one or both or none of these is extraneous. One more step here. Getting the answer itself is not enough. You've got to plug it back in. So we plug it back in to check for those extraneous solutions, and we end up with 2 that work. When I plugged in negative 4 and did the math, I got 8 equals 8. That's correct. That's true. A true statement. It worked out. It was a solution. When I plugged in 3 to both sides and did the math, I got 1 equals 1. Well, that's a true statement, so I know that it worked, right? What is a solution? It's a value for x that we can plug into the function or to the equation to make it true. We've done that with both of these. So in this case, there are no extraneous solutions. Both answers work. We have 2 answers, 2 solutions that we're going to count, negative 4 and positive 3. Got a few more examples, and these are going to look a little bit different. If we haven't talked about this yet in class, I want to share with you that square roots are the same thing as rational exponents. So if I have a square root of x, it's the same thing as x to the 1/2. If I have a cubed root of x, it's the same thing as x to the 1/3. And we'll play with this a little bit more as we get further into this unit. But anytime you see a square root or an x to the 1/2, you should know that those are the same thing. They're just written differently. So when I see in this example here, 5x plus 7 in parentheses raised to the 1/3, this is exactly like a cubed root. right? So we're going to solve it exactly like we would a cubed root. We're going to raise both sides to the power of the index. Well, in this case, that's raising both sides to the denominator of the 1/3. So 5x plus 3, 5x plus 7 is going to be raised to, or the cubed root of 5x plus 7 is going to be raised to the 3rd power. And 3 is going to be raised to the 3rd power. You have to cube both sides. Well, that gives us 5x plus 7 equals 27. We subtract 7, divide by 5, and we end up with 4 as the solution. When you plug 4 back up here, 5 times 4 is 20. 20 plus 7 is 4, and the cubed root of 27 is 3. So we know that it works. It gives us a true statement. In example 9, we have 2x equals 4x plus 8 in parentheses raised to the 1/2 power. We're going to square both sides because this is really the square root of 4x plus 8. And when we square both sides, 2x squared, you have to square the 2 and the x because there's multiplication between them. We square them both, so that's going to be 4x squared. And on the right side of the equal sign, I did not change this to a square root of 4x plus 8 this time, but when you raise a power to a power, you multiply, don't you? Well, what's 1/2 times 2? It's just 1, which is how those powers cancel each other out, leaving us with just 4x plus 8. Notice we have a quadratic. What does that mean? We've got to treat it like a quadratic, get everything to one side of the equal sign. Since the 4x squared is already positive, I'm going to subtract 4x and subtract 8 to the left so that I get everything on one side of the equal sign. Before I factor, notice that there is a common factor here, a greatest common factor of 4. So we're going to divide all 3 parts by 4. That leaves us with x squared minus x minus 2, which we then can factor to give us x minus 2 times x plus 1. Now this 4 has been factored out. It is one of the factors, but since it doesn't have an x, it's not going to influence one of our solutions. So we kind of ignore it. We set it equal to 0, it doesn't give us any information. But x minus 2 equals 0 and x plus 1 equals 0 give us 2 solutions, 2 and negative 1. Now since I've squared both sides, there is the chance here that there's an extraneous solution. So I need to go back and plug them both into the equation using substitution to check for those extraneous solutions. When I plug in positive 2, I end up with 4 on the left and 4 on the right. Remember, this is like 16 to the 1/2 you can use your calculator for, but it's the same thing as the square root of 16, which is 4. It works. When I plugged in negative 1, though, I ended up with negative 2 equals positive 2. That is an extraneous solution. Extraneous solutions are not counted. They don't work. So the only one that's going to work is the positive 2. That's the only thing that we plugged it in and gave us something good. All right, example 10 is going to be our last example today. There are different ways to do these. I don't want you to think that the way that I show you is always the only way, but there are good ways. For example, on this one, you could divide both sides by 3 first and then square both sides. It's also okay to just go ahead and raise both sides to the power of the reciprocal of 1/2 or to the second power since it's raised to the 1/2. Remember, when you raise things that are multiplied together to a power, you have to raise both of them to that power. So 3 squared is 9. X plus 6 to the 1/2 power squared is x plus 6. 9 squared is 81. Every part has to be raised to the second power. We're going to distribute the 9 to give us 9x plus 54. And then solve this equation by subtracting 54 and then dividing both sides by 9. That gave us x equals 3. We have solved for x. It's the only solution that we got. We plug it back in to see if it's correct, so we end up with 3 plus 6, which is 9. 9 to the 1/2 is 3, and 3 times 3 is 9, so I know that it worked. All right. Checked it. I can circle it, put my stamp of approval on it. I'm good to go. Well, that is it for today. Lot of examples to go through, and I'm sorry about that, but there's several different types, and I wanted you to see a few of each of them. As you're working through these in class over the next few days, ask questions if you are running into any trouble or you want some help or some one-on-one, and I will see you in class.